This lecture is going to introduce you to electric circuits and Ohm's law. This is consistent with your textbook reading as you see here. To start off, we're going to look at the flow of charge, chapter 34.1 in your textbook. When the ends of an electric conductor are at different electric potentials, the charge flows from one end to the other. Charge flows when there's a potential difference, as provided here by the battery, or the difference in the potential, what we'll call voltage, between the ends of a conductor. This is what pushes current in wires, the potential differential. So the greater the voltage, the greater the amount of current you're going to get flowing through a circuit. You can think of it like this situation right here. Water flows from a higher pressure to lower pressure. That's always true. The flow will cease when the difference in pressure ceases. Location B, we see that water continues to flow because of a difference in pressure and is maintained with the pump. Even though it's flowing here, you're getting water pumped back to the top. So water flow will be from the high pressure to low pressure. Well, that's the same concept of what's happening in a battery. You're getting your cathode and your anode here. It's pushing current from high to low. So what is electric current? Well, electric current is the flow of electric charge. In solid conductors, or wires, electrons carry charge through the circuit because they are free to move throughout the atomic network. Protons are bound to the atoms within the nuclei, but atoms are not fixed. In this case, so they can move when there's a push from the electrical potential difference. Essentially, the battery and the voltage is pushing them. And when I describe atoms, really I should say electrons. Current is simply measured in amperes. Amps are the symbol A. So we can see it this way. In this picture here, we're seeing current that's electrons that are already in the wires themselves. They're flowing in this direction. We say from cathode to anode. Think of it this way. The flow of charge. The electrons are already in the wire itself, the conductor. So when the rate of flow charge passes this section, which is 1 coulomb, right, this is 6.24 billion electrons per second, the current is 1 ampere. It's simply just showing you that current is flowing, and this is a cross section of the wire. Current is flowing from kind of left to right. It's simply flowing here. The electrons are already there. The battery is providing the push, and that's what we call voltage. So what is voltage? Well, voltage sources are something like this. So something must provide the potential difference in a circuit. Batteries and generators provide a voltage source. So there's often some confusion between charge flowing through a circuit and voltage being impressed across a circuit. So in the water picture, think of it this way. If a tube of water, a cylinder of water, is sideways, there's no height difference, so water doesn't flow. We could say that there's no voltage in the circuit, right? There's no voltage, so no charges flow. But as soon as you tip this up or lift this up, we get a height difference that causes water to flow downhill. So the battery provides that voltage, so charges flow. It's essentially the equivalent in the pictures here. The voltage is like lifting it up. You have a potential difference, so it's going to flow downhill. So you have your cathode and your anode, and current is going to flow in the circuit because battery creates a voltage difference. So water will only flow if there's a difference in gravity in the two cylinders, where water flows downhill toward the lower end, from the higher end. So using this water analogy, similarly charges flow, or current, through a circuit because voltage is applied across the circuit. That's what your battery is doing. Voltage causes current. Electric current provides energy for light, among other things. So in this case, we would say the current is flowing this way. We would call that clockwise. So what is resistance? Well, the amount of charge that flows depends on the voltage provided by the source. For example, two batteries provide more voltage and thus more current. The current also depends on the resistance of the flow within the circuit. So the resistance of a wire, or the resistor, depends on the conductivity of the material used in the wire, or the thickness of the wire, and its length. Think of it this way. Let's go back and just look at this water piece. If I have this container of water that has a small opening, you're going to get a slower rate of flow. There's going to be a higher resistance. It's going to decrease current. But if I open this up and make this larger, more water is getting out. So this would be a lower resistance, and we'd have more current flowing. We'd simply say that more water is flowing out of here. Thick wires have less resistance than thin wires. Long wires have more resistance than short wires. Electrical resistance is measured in ohms and is represented by the symbol, in this case here, omega. It's this symbol right here. For a given pressure, more water passes through the large pipe than the small one. Similarly, for a given voltage, more electric current passes through a large diameter wire than a small diameter one. So we call thickness of wire what's described as called gauges of wire. And that brings us to Ohm's law. This is the relationship among voltage, current, and resistance that we describe as Ohm's law. Ohm's law states that the current in a circuit is directly proportional to the voltage across the circuit. and inversely proportional to the resistance of the circuit. So it's essentially saying that voltage equals current times resistance, as this picture shows. Ohm's law will be used to quantify how much of something we are trying to measure. We see that voltage, current, and resistance are all related, and by how much. So a quick summary. Voltage is measured in volts, or capital V. Current is I, is measured in amps, capital A. And resistance, R, is measured in ohms, omega. So let's solve a couple problems. Ohm's law, in this case, we're talking voltage equals current times resistance. So observe the circuit to the left. A battery provides the chemical energy to push current through the wires, or the circuit. The current in the circuit is 1.5 amps, and the bulb has 1 ohm of resistance. So what is the voltage of the battery? Well, to answer this, we must apply Ohm's law. Voltage is going to equal the current, that's given 1.5 amps, times the resistance of 1 ohm. But since we are solving for voltage, we have to multiply current times resistance. So I multiply 1.5 amps times 1 ohm, and you'll find that 1.5 volts times 1 ohm is 1.5 volts. That this here is a 1.5 volt battery. Let's look at this a different way. So we'll use the same picture. A 1.5 volt battery provides the chemical energy that pushes current through the wires, or through the circuit. The light bulb has 1 ohm of resistance. So what is the current in the wire of the circuit? So to answer this, we still apply Ohm's law. Voltage equals current times resistance. But since we're solving for current, we must divide voltage by resistance. Here I see current equals voltage divided by resistance. I have 1.5 volts given. I have 1 ohm given, so 1.5 volts divided by 1 ohm equals 1.5 amps of current. There's 1.5 amps of current in this picture. And this picture here looks like this is a cathode, so current would be traveling counterclockwise. So let's do another problem. So here I've given you a little different graphic. I have 2 light bulbs, 2 resistors. They have 1 ohms of resistance, and I have a single battery here. So observe the circuit above. A 5 volt battery, so this is 5 volts, provides the chemical energy that pushes current through the wires of the circuit. Each bulb is 1 ohm of resistance, as given in the picture. So let's answer the question. Is the circuit open or closed in the picture? Well, there appears to be a closed circuit, right? Closed. So what's the total resistance in the circuit? Well, I have a 1 ohm resistor and a 1 ohm resistor. Well, I simply just add those together. 1 plus 1 equals 2. What direction is the current flowing? Well, let's see. Cathode to anode tells me it's going this direction. We call that clockwise. It goes from cathode to anode. That's the conventional method. So what is the current of the circuit? Well, current is going to be voltage divided by resistance. I have 5 volts that's given, divided by 2 ohms of resistance, simply 1 plus 1. I've got 2 ohms. 5 divided by 2 is 2.5A, or 2.5 amps of current that's flowing in this circuit. Let's do one more. Once again, Ohm's law, we're solving problems. I have a new picture for you. So let's say each battery is 3 volts. Notice I have 2 different batteries, so I have 6 volts total. It says each battery is 3 volts. So what's the total resistance? Well, I have 2 ohms here, 2 ohms here. I have a total of 4 ohms. What direction is current? I have my cathode on top, my anode on bottom, so therefore I'd say it would be flowing clockwise, right, from cathode to anode. That's the conventional method. So what's the current of the circuit? Well, current is going to be my total voltage. That's going to be 6 volts, right? I have 2 3-volt batteries, so I have 6 volts divided by 4 ohms, which shows me that I have 1.5 amps of current flowing in this circuit.